Good afternoon, sir.
So, need to discuss today is a very important part of current day's research on decision tree, that is begging and boosting. I hope you all are aware of it, right? And yesterday also, I think Ankit again message in the group. Okay, so let me briefly introduce some facts about this begging and boosting. You know the decision tree. We have gone through a lot of different versions of it, like card, ILT, okay, J45. A lot of different versions exist. The important, or you can say that why you have selected decision tree for the classification tag, then obviously you will say that this is simple to implement it, right? That is the reason why we have gone for choosing the decision tree. But problem is that you already know that some problems like overfitting, they might occur while growing this decision tree. Okay, so also there is a problem like bias or bias and variance. This bias for simple trees, and for complex trees we might face some variance problem. And I hope you know that what is the meaning of variance. Okay, how the actually data points being represented. Okay, so they are the problems. So we always try to improve the algorithm that do exist previously. That is the main aim of research, right? You also doing your research projects now. You get to know that how to go for that. But in case of decision tree, when we go for improving this performance or efficiency, then there is a popular method that is known as ensemble method, right? You should note down that ensemble method. This is the way by which we try to actually improve the decision tree's performance and efficiency. And the concept is very simple. The concept that we use in the case of decision tree, I mean ensemble method of improving decision tree, is that we try to combine many decision trees. Okay, and to find out that performance is better for which one, or sometimes by combination of several trees, we go for one prediction that will be, of course, more accurate than a single decision tree can give it to you, right? One sentence is there for ensemble method that you know, you have to know, already know. Is a group of weak learners come together to form a strong learner. बहुत सारे लोग एक साथ हम क्या कर सकते हैं? Suppose कुछ चीज हम सीख रहे हैं, we are learning, we are at the stage of learning, then what would happen? By making a group, we can uh, perform better than individually we go for it, right? So when we talk about the ensemble method, then there are some techniques that to be noted down under it, and one is bagging, another is boosting that I have given for this discussion. Okay, bagging and boosting. Of course, random forest is there. Random forest I have already actually discussed. Right. Random forest is what? That is also a way to improve the performance of decision tree, right? Yes or no? Are you
Yes,
guys
sir.
listening to me? Yes, am I audible
Yes,
there?
sir.
Okay.
Yes, sir.
Yes,
Yes,
sir.
sir.
So this Ansible method that I have mentioned, you can consider that random forest is also part of it. Okay, but mainly we refer two techniques, that is begging and boosting. And begging, the term derived from bootstrap aggregation. Okay, and in this case, we try to reduce the variance. Variance means you know that. What does the term variance means in our statistics? Okay, we try to reduce it. Okay, so variance कब आएंगे? जब डाटा सेट्स में स्कैर्सिटी बहुत ज़्यादा है, या तो आप बोल सकते हो, जो आप क्या ड्रॉ कर सकते हो, एक प्लॉट this data processing के समय पे ड्रॉ करके देख सकते हो. Either you go for histogram, or there is a very important visualization technique to see that how data points are distributed. Can anybody tell me which one that I'm referring now? एक प्लॉट है जो हम यहाँ प्री प्रोसेसिंग में यूज करते हैं, ये देखने के लिए
Plot, scatter.
Very good, right answer. So that is the scattering plot, or that to see that how data points are being actually distributed, right? So to have an idea about the variance, of course, you need to go through that. Now, in the case of this bootstrap aggregation, we try to create many subsets from that main training sample. Okay, that is being chosen randomly. Randomly means ऐसा नहीं है कि मतलब कुछ भी आप उठा रहे हो, इसके लिए भी कुछ टेक्निक्स है कि how you go for choosing them. Okay, then उस जो several subsets हमने create किया, we try to train them individually with the decision tree. Okay, and after that we will do what? Ensemble of these different models for different subsets, and then we take the average. Okay, and that average, of course, will be more better performing than the single individual one, right? That is the main concept behind bootstrap aggregation or bagging. So ये अगर आप अच्छे से देखोगे, if you analyze it carefully, then you will see that what actually doing is a kind of random forest development, right? Random forest में यही करते हैं. But यहाँ random forest में एक चीज हम extra करते हैं. We go for doing some extra fact with the in case of random forest. Okay, क्या करते हैं हम? यहाँ वो bagging में आपने देखा, we try to create several subsets from the training data set, but we are not considering the features selection part. If we go for random feature selection part rather than all the features, then that bagging will become random forest. Okay, are you getting me? यही difference है
Yes,
bagging
sir.
और random forest में. So you can say that random forest is a kind of extended part of bagging. Bagging, we go for dividing the data set into several data sets. Data sets I'm referring is obviously the training one, and we go for each for a different decision tree. Then we go for selecting the average one. And but in the case of random forest, besides dividing the data samples into different subsets, we also do one more fact, that is randomly selecting the features. That is bagging. Okay. Then we have boosting. Okay. Boosting, from the name itself, we try to boost the performance. Right? Boosting मतलब हम क्या समझते हैं? हम क्या कर सकते हैं? उस परफॉर्मेंस को बूस्ट करना है. Okay, we try to improvise this means the performance of this decision tree. So how we do the boosting and how it is different from bagging, I hope that someone of you will consider this fact while discussing this, while presenting the discussion on this bagging and boosting. Okay. So in case of boosting, we go sequentially, step by step. Okay. One, in simple word, I can say that you actually try to improvise yourself from learning from the errors. आपको ये तो समझ में आ रहा है, हमारे पास डिफरेंट डिसीजन ट्रीज है, तो आप ये देखोगे कि किसमें ज्यादा एरर आ रहा है. ओके, एंड where the error is found maximum, you will give maximum weight to that, so that in the next sequence you will focus on that and you will try to reduce that error. ओके, तो पहला जो प्रायोरिटी था उसमें जो एरर मिल रहा था, जिसमें ज्यादा एरर मिल रहा है उसमें आप ज्यादा फोकस कर रहे हो, उसमें ज्यादा मैक्सिमम वेट पुट कर रहे हो. नेक्स्ट सीक्वेंस में उस एरर को आप रिमूव करने की या तो कम करने की कोशिश कर रहे हो. राइट, that is boosting. And in case of boosting, we maximum times use gradient descent algorithm. ओके, ग्रेडियंट डिस्टेंस एल्गोरिथम आप लोग जब ये करोगे, प्रैक्टिकल करोगे, देखोगे ग्रेडियंट बूस्टिंग नाम के एक है. सो देयर वी यूज ग्रेडियंट डिसेंट फॉर द बूस्टिंग पर्पस. So that is about bagging and boosting, and they are under our ensemble method. And you have also seen that random forest, a kind of extension of the bagging. I hope this picture is now clear to you and clear to everybody, right? Yes or no?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
now handing over this session to Ankit to smoothly conduct the discussion. So we may begin now. Thank you.
Okay, so good afternoon, everyone. So today's discussion topic is about boosting and begging. So let me start first, then others can randomly raise their hand and can present their PPT. Now it is visible, right?
Yes, it's visible.
Oh,
Yes.
okay. So let's start. So I have shorted some of the important points that we have discussed in my content. So including the implementation part. So first that um, the most important, that is the part which is assemble learning. So bagging and boosting these are the parts, these are the methods of assemble learning. So assemble learning, why assemble learning? We have to improve the machine learning model performance by combining several methods, and this approach for bagging. So bagging and boostings are similar in that case that these both are assemble technique, where we set the weak learners. In both technique, we are setting the base estimator. We can take any method, any algorithms that we think like we can boost their technique, we can boost their performance or accuracy. We can put it on the base estimator to improve their, to make it a strong learner, or to obtain a better performance. So the basic idea behind this, we are setting the classifier to provide us the better performance in this assemble learning. So we have two types, that is bagging and boosting. We but the may and we may also face errors. So in what it do, it helps to decrease the model's variance, and in boosting it helps to decrease the model bias. Okay, so actually these are the main cause of errors in learning. There is one more, that is noise is also there. So noise, bias, and variance. So assemble learning helps to minimize these factors. By using assemble methods, we are able to increase the stability of the final model and to reduce the errors, like this I have mentioned, bias and variance. So bias bias describe how well a model matches the train set. When we provide our training set, sometimes sometimes happens like that, if there is high bias, it won't match the data set closely. Fine. Well, if the model have a low bias, it will match the data set. It will match the data set, and bias come from the model that are overly simple and fail to capture the trend present in the data set. And and in variance, it describe how the model changes when we train it using different portion of the data set. See, typically, actually, models with high variance have high bias have low variance, and the model which have low variance have which have high variance have low bias, because see, these both are from the opposite types of the model, isn't it? One is from this begging part, and one is from boosting part. So like there is this condition is there, like with high bias, low variance, and vice versa. Okay, so so next is the bootstrapping. So see this figure, fine. So what is bootstrapping? Actually it refer to the random sampling with the replacement, and bootstrap allows us to make the understanding better about the bias and variance within the data set. Okay, so in bootstrapping, what we try to do is we use sample technique in which we create the subset. Okay, subset of the observation from the original data set. Okay, like as I told that it involved random sampling. Okay, then the selection of all the examples in the data set have equal probability for selecting by the algorithms. And so this method also help for what, for better understanding for mean and standard deviation from the data set. See, when we try to describe, you can use describe function, right, to get the mean and standard deviation. So mean value and standard deviation value can say very much thing about the data set, or the suppose in particular attribute you have lots of two or three, in particular attribute you have two or three difference value. So if you use mean and standard deviation, then you can understand what actually the value, how much weightage is there, how much weightage is the element is providing to us. Like then we can use it for analyzing it. So now it is about the begging. So see, I have explained about bootstrapping, because begging is also known as bootstrap aggregation. Okay, so begging is the application of bootstrap procedure to a high variance machine learning algorithm, that is example decision tree. Okay, and the idea behind the begging is combining the results of the multiple model and get the generalized result. uh, Generalized result. Okay, so in begging technique, what we do is we use the subset, that is bags. Okay, to get the fair idea of the distribution. That is the complete set, and the size of the subset created from the begging is less than from the original set. Fine. So this is what represented in this picture. Then how it work? Have a look. This what I did here is like in this picture is that there multiple subsets are created, isn't it? Multiple subsets are created from the original data set. Then it's selected from the observation with replacement. Okay, now what happened in the next step, what we will do, like the bag, you can say the weak is created on each of the subset. Then the model run in parallel, or you can say independent of each other. Fine. Then the final prediction are determined by combining the prediction from the model. Okay, so this is what is represented in this picture. So the next part is the boosting. Okay, the pictures is okay. So boosting is a sequential process. Why? Because what we try to do here is we in each model and subsequent model we try to correct the error of the previous model. Okay, then the succeeded model are dependent on the previous model. In this technique, the learner are learned is sequentially with early learner fitting simple model of the data, and then analyze the data or errors. Okay, in other words, you can say like if we feed consecutive tree and then random sample at every step, the goal is, what will be the goal? Our goal is to solve the net error. Fine. So look at the figure 3. So here in the figure, okay, in the figure 1, let me show you here. Okay, so here at first what we do, a subset is created from the original data set. Okay, a subset is created, then initially all the data points are given equal weightage. You can see like here all the data points are given equal weightage. Okay, then the base model is created. is used to make the prediction of the whole data set. And in the figure here, in the figure 2, errors are calculated using predict actual value and the predicted value, and the observation which are incorrectly predicted are given higher weightage. See here the three misclassified, that is the blue color plus sign. You can see that it is giving the higher weightage, so it is appearing like big, like. So here what we are trying to do in the figure 3 is we are trying to give the higher weightage on the error. Fine. Then in the last part, what we do is we simply in the here what we do is like we simply multiple models are created, each correcting the errors of the previous model. Then we get the final model. Fine. Then we get the final model of all the weak learners, you can say. So does the we can say that the boosting algorithm combine a number of weak learner to form a strong learner to get better performance. Fine. So here so getting n learners for bagging and boosting. So what we do, we try to generate the additional data in getting the and for getting the n learners. By we what we do, we generate additional data in the training stage. Okay, so n new training data sets are produced by random sampling, as I told earlier. So by sampling with the replacement, some observation may be repeated in each new training set. So what happened? in case of bagging, any element have the same probability to appear in the new data set. But in boosting, the observation are and or the weightage are therefore some them will take part in the new set or more often. And these multiple sets are used to train the same learner algorithms, and therefore different classifiers are produced. Fine. So about the weightage data element, what is this weightage element that we try to let me give the difference between this method. While training stage is parallel, in training stage is parallel is for pegging, like that is each model is built independently, isn't it? So the boosting build the new learner in a sequential way. uh, so in the boosting algorithm, each classifier is trained on the data, taking into account the previous classifier. So after each training steps, what we do, the weightage are redistributed. Okay, the weightage are redistributed, and misclassified data increase the weightage of the weightage to emphasize the most difficult cases. So that is what are picturized in this figure. Next is okay. Now the classification is stage about the so here, see, as I have told about the n learners. Okay, so to predict the classes of the new data, what we do, we only need to apply the n learners, or you can take n learners to get what, to get the new observation. So in pegging, the result is obtained by averaging the responses of the n learners, or you can say majority voting. I will show you in practical. I have done the practical, I will show you. And in boosting, what we do, we assign the second set of weight, the time of the n learner classifier, in order to take the weightage average of their estimation. Okay, this is simple. This is only what I have pictured. And what I will say more, okay, this boosting techniques, for example, the gradient is there, and one more is there, that is adaptive boosting, there is ada boost. uh, in ada boost, what happened, like if the error less than 50%, it required the 50% error less than 50% is required to maintain the model. Fine. Otherwise the iteration is repeated until the achieving the learner uh, better than the random case. And about the iteration, I will show you what is the how the it takes place and all. So now the question is when to select, and how, whether to select this bagging or boosting, and why. So it will come to your mind, isn't it? So it depends. Fine. I've given the point like it depends on the data in the simulation. Like sometimes what happen, um, if there is lots of unclassified, or if there is mean if there is outliers, like if there is no properly like data, if imbalanced data, then you can check it practically. Like adaptive boosting don't give that good result. Fine. So what is the main part is that like if the problem is that the single model, what we get very low performance, we get very low performance. So in bagging, what we do, we rarely get a better bias, isn't it? So however, in boosting could generate a combined model with lower errors, as it optimize the advantage of reduce the pitfall of the single model. So if the single model provide us the low performance, then instead of applying pegging, you can apply boosting to optimize the result. And if suppose if we get overfitting, suppose sometimes happens that it gives you 100% accuracy due to overfitting, then you can, after using bagging technique, you can see that the accuracy is decreases, like it will give you the accurate result. So then you can go for bagging to avoid this overfitting. You can go for this. Fine. So you can also say that like for bagging is more effective than boosting. And the thing is that boosting is more vulnerable, vulnerable to overfitting than bagging. Like as I told, as I given the example. So similarity, there are lots of similarity. Like both are the assemble methods, and we assemble learners. And I will show you practically this type of. I've just summarized the what I've explained. I've summarized the similarity between the bagging and boosting part, and there's no nothing to explain. Like so, in here I have included some of the difference. Like in bagging, what we do, we try to combine the prediction, isn't it, from the reference model, and in boosting we try to predict that belong to the difference type. And in bagging we try to decrease the variance, and in boosting we try to decrease the bias. Okay. And bagging we give each model, we give equal weightage, whereas in boosting we try to give the weightage according to their performance. And in bagging each model built independently, whereas in boosting new model are influenced by performance of the previous model built. So these are the some of the difference. And see, bagging solve overfitting problems. So in case of overfitting, if you use boosting, then you will get not get any, you will not get result, right? And after 100%, what you will get if you apply boosting. So you can apply bagging for this. So bagging is a technique extended for random forest model, and boosting is the extended for gradient boosting. So okay, so I have applied, I have used this MNIST dataset actually. So just to show you here, what I did is, you can see. So these are the handwritten standard dataset. A standard dataset is there in the MNIST. I have not installed Keras. You can, if you have installed Keras, then you can directly import it, or otherwise you can do one thing. You can download it from MNIST website. It is available. So in the implementation part, I've implemented the assemble bagging boosting. So how it's work, you can see that. First, I have imported the NumPy and pandas, okay, for numerical and all. So see, these are the label. I have what I have, you can visualize that 28 into 28 is the pixel, and the labels are there. Fine. लेकिन देखो जो डाटा सेट में एक्चुअली है ये सब है. Like if you import keras, you can see this. Fine. Or you can use matplotlib library also to visualize each numbers by applying different code. So next, what I did, I have just there is two. Okay, fine. When you will download, you will see there is separate train CSV and test CSV. So you can check their shapes and all. So what I have imported decision tree. So I have imported random forest, bagging, AdaBoost. I have used here adaptive boosting. Fine. If you want to use gradient, then you can go for regressor. Fine. Then I have used voter classifier to combine all the some of the classification algorithm. Okay, so I will check the accuracy through the metrics, accuracy score metrics. So what I did the next step is I have slice. You know this iloc dot this one. This is slicing method. Okay, this is slicing method. If you go through data structure, then you will understand this. This is a slicing method, and in iloc, what it do actually, we select iloc is in panda select the rows and columns in number. Fine. So here column one is there, like the after the second column, then next in the training set what I have fine. Like white training set in df iloc is 0, that is that means label I'm using the last row of the no, not the last frame after, it will be included on our training stage, and we will use our different classifier. So what I did distinct, then you can see the what is the accuracy is 87% or 88%, you can say. And in the assemble model, I have included the random forest because there is a combination of various decision tree. So I have taken the n estimator 10 and I have predicted. So see the accuracy have improved. That is 95. Fine. The next in the bagging. See in the bagging, if you I think if you don't give decision tree also, in by default it will choose the base estimator as decision tree. If you want to give different classifier SBM KNN, you can provide it. Fine, you can apply it. Just give this one base estimator equal to KNN SBM. Anything you put, it will work on that basis. Fine. So after applying bagging on the training set, what I've got 95% accuracy. So in the boosting part, what I have used adaptive boosting classifier. So the accuracy is not that much improved. Like it is showing like 0.8, 0 point negligible accuracy, because in decision tree you have got 87, 88%. Fine. So next I have applied voting classifier. So in the voting classifier, what happened? The particular model which is trying to give the better result, can get the better result through by using this. So I have included this one, a logistic regression decision tree, SVM and KNN. And please give the max iteration, otherwise it will show warning. Fine. And about the solver, this one is LB FGS is default. By default you can use, or you can use Newton's easy. You go through the documentation part, then you will understand that why LBFS like this. Provide the max iteration properly, otherwise it will not run and it will show error. Otherwise the model will not fit actually. So after applying the voter classifier, I have provided the training set, then it is giving 93% accuracy. So after comparing the result, what I've got, that random forest voting classifier and pegging classifier is giving better result. Or you can see here that the pegging classifier have given 94, and random classifier have given 95% accuracy. So this is how you can apply. So don't go for iris dataset. You can try for this one, cancer dataset. It will show you nicely. But iris dataset, you can try in iris dataset, but when you do like you boost the technique, boost the algorithm, like it will not show that properly the accuracy. Like you cannot differ so much. Like if you use this MNIST, then you can see the difference properly, or you can use the cancer prediction data set. Fine. So thank you. This was my discussion.
I must say that Ankit, you have presented very well, and the analysis part is really very, very good. Okay,
Thank you,
that's a
sir.
very nice presentation, and first part, I must say that this is really of PG standard now. I can say that. Thank you, Ankit.
Thank you, sir.
So good afternoon, everyone. Let me share my screen. So today's discussion topic is bagging and boosting. Um, and the contents are introduction to ensemble methods, then why to use ensemble methods, when and where to use it, then popular ensemble methods, the bagging and boosting. So let's first start with the introduction. Bagging and boosting are, before going to ensemble method, let's just go through the overview of it. So bagging and boosting are similar in that they are both ensemble techniques where a set of weak learners are combined to create a strong learner that obtains better performance than a single one. Now let's see what is an ensemble method. Ensemble method is a machine learning concept in which the idea is to train multiple models using the same machine learning algorithm. The ensembles take part in a bigger group of methods called multi-classifiers, where a set of hundreds or thousands of learners with a common objective are fused together to solve the problem. The second group of misclassifiers contains the hybrid methods. They use a set of learners too, but they can be trained using different learning techniques. Stacking is the most well-known. The main causes of error in learning are due to noise, bias, and variance. Ensemble helps to minimize these factors. So now, why to use ensemble methods? It because it gives better accuracy, that is low error. It has higher consistency, that is avoids overfitting and reduces bias and variance errors. Now, when and where to use ensemble methods? Um, Single model overfits, that is, for example, decision tree. So you can use random forest. If results worth extra training, then using ensemble methods are better. Can be used for classification as well as regression. Now, there are the popular ensemble methods are bootstrap aggregation, also known as bagging, and boosting. So, bagging. Um, in bagging, multiple models of same learning algorithms trained with subsets of dataset randomly picked from the training dataset. So in this, we take a dataset and divide it into training dataset and testing dataset. And then after that, from the training dataset, we randomly select data points row one by one into the bags repetition and the repetition is allowed. So here we can see in this picture that after the random sampling, we are dividing it into subsets of the main data set, that is the training data set, and then giving the training data set to the model, that the classifier, it can be any classifier if you're using decision tree or anything. So after training the model and after that, we are taking the results of it and taking the average or the voting of the results, and then we finally get the results. So next, boosting. This is a little variation on bagging, selecting points which gives wrong prediction. So here we are selecting those points, like in this technique, we usually focus on the wrong predictions. So we go for the weak learners. So in order to improve accuracy, this helps in teaching the ensemble model the points where it usually goes wrong. This results in huge a huge accuracy, but also tends to overfit and increase in variance. So let's see how it works. So here we are taking a dataset again and then dividing it into training and testing. And then from the testing dataset, randomly selecting points one by one into the bag, and then putting it in the model, and then testing the model using training dataset, and the results that we're getting as data points with wrong prediction. So again, we are taking it as the input for the next model, and we give the training data set there also. And after that, we are again testing it with the training data set on Ensemble with the both models there. And then again, if the data set data points with wrong predictions are coming, then then it will again go on repetition. This process will repeat till the predictions gets right. So that's it. Thank you.
So, good afternoon, everyone. Ankit, can I start?
Yes, yes,
Okay. So, good afternoon,
yes. You can
everyone.
share.
Okay. Okay, let me share the screen. Ankit, is my screen visible?
Yes, it is visible.
Okay.
Please start.
So, today's discussion topic is bagging and boosting. So, before jumping into that, I'll be telling some. I'll discuss about ensemble methods. So we all know about decision tree technique, right? So that is basically used in our day-to-day life to make decisions. Many organizations use this supervised machine learning technique to make a better decision that would help them to generate more surplus and profit. So many Ansible methods combine different decision trees to deliver better predictive results, where more models are used to make decision and thus consider the output not by using only one model. So the main principle behind this method is that a group of weak learners come together to form an active learner. Okay, so let's understand it with the help of a diagram. So this L1, L2, and L3, just is my pointer visible? Ankit? Hello?
Yes.
Okay, so
Hello.
uh, okay. So here we can see L1, L2, L3. So it's actually it's the base learner, or we can say it as a weak learner. So that are trained by the training set. So and this base learner can use different algorithms. Let's say L1 uses naive Bayes, L2 uses linear regression, and L3 uses SVM, and so on, as to make different diversity of the output. So in other words, we can say it as a heterogeneous ensembles, because if one algorithm is used, diversity is reduced. So we can say that different algorithms leads to greater diversity. The output generated using different algorithms, like let's say in this case we can see L1, L2, L3. So this all are combined to form the strong classifier. And this strong classifier will provide more better results, and it's as there are greater diversity of algorithms included here as compared to this single. So now let's come to bagging and boosting technique. So a bagging technique. So this technique is used when our goal is to reduce the variance of a decision tree. So here the concept used is to create a few subsets of data from the training sample that is chosen randomly with replacement. Now each collection of the subset data is used to prepare the decision tree. Thus it ends up with an ensemble of various models. So thus the average of all the assumptions from the numerous trees is used that becomes more powerful than a single decision tree. So now let's understand it with the help of a diagram. So firstly, starting from the original training data that contains different training samples. So let's randomly take some samples with replacement, which means that a particular record can be present in more than one dataset. That is, a particular record can be present in either D1, D2, D3, so it can be in any dataset. So using that, we create a dataset, say D1, D2, D3, or we can also say it as a bootstrap sample, and so on. These datasets are generally random samples taken from training data. So after that, classifier is created for each sample. So this bootstrap sample D1, D2, D3 are created to train the classifier based on this sample. So now similarly, each classifier are trained and these all are combined. So after combining, we get a strong classifier. So it is referred as strong classifier as its predictive power is strong compared to the weak classifier, and its error rate is also less. So here weak classifier is this C1, C2 and C3, and strong classifier is this one. So this result in more accurate as compared to C1, C2 and C3. So now let's say we take an example, say we get a classification problem and say we have two classes, class 1 and class 2, assuming the test tuple data as X that is given to each weak classifier and C1, C2, C3. And this classifier are asked the question whether this X tuple is located in which class, whether in class 1 or in class 2. Let's say C1 has told that this X tuple, test tuple, belongs to class 1. This C2 told that it belongs to class 1. C3 told that 2, and so on. So now the strong classifier will use a voting mechanism to check to see which class has got a maximum vote. So here from this diagram, it's clearly visible that maximum vote has been got by class 1. So this depicts that the X variable belongs to class 1. So we can say the data belong. Okay, so thus the strong classifier uses this voting mechanism whenever there is a classification problem that arises. So now let's come to this boosting technique. So boosting is another ensemble procedure to make a collection of predictors. So in other words, we actually fit consecutive trees, usually random samples, and at each step, the main objective is to solve net error from the prior trees. So if a given input is misclassified by theory, then its weight is increased so that the upcoming hypothesis is more likely to classify it correctly. By consolidating the entire set, at last converts weak learners into better performing models. So now let's understand it with the help of a diagram. So here D is the training set, training data that may contain many records instances. Let's say this data contain instances 1, 2, 3, and so on, and corresponding weights to it. And this all weight and all this W1, W2, W3 all are of equal weights, which means that each instances will have are capable to be selected by each data set, that is D1 sub data set, that is D1, D2, and D3. Let's say this subset D1 randomly selects a 1, 3, 7 from this data, from this training data. So these instances will be used to train this model M1. So after that, to check whether this M1 is correctly like classifying its class or not. So after that, all this data will be used and will be checked. So let's say M1 model wrongly detected 463. Wrongly detected the classes of 463. So in that case, what data do is that it will increase the weight of this 463 so that it can be used by the next subset. So now when D2 started its working, so it has to select random samples, right? So it will choose the instances that has more weight. So it has seen that 463 has more weight, so wrong weight uh, okay, so it has selected 463 because it has more weight. More weight means it has been wrongly detected, wrongly classified by M1. So it has to be trained by this D2 to this model M2 so that it can easily classify, correctly classify these instances. So for that, this 463 will be used to train the model M2, and after that, all these instances will again be used to check M2, and so on. It will be continued so on. So in the next also, it's seen that it wrongly classified this 237. So again, it has increased the weights, and similarly, it will continue. So at the last, the output will be combined of all the models will be combined, and it will form the strong classifier. So let's say but to test, earlier we used the instances from the training set, but now let's say a y variable came that belongs to a test data. So now these y variables are given to each model, and to check whether the model is able to correctly classify its class or not. So let's say m1 told that this y variable test tuple belongs to class 1. Let's say this m2 told that this y test tuple belongs to class 1, and so on. So here also the voting mechanism will be used, and thus we can see that this strong classifier seen that y belongs to class 1. So that's it. Thank you.
Okay, so the session end here because the time is up. And thank you everyone for participating and attending the discussion.
Thank you, Ankit, for beautifully conducting the session, and all who have participated and who could not participate due to the lack of time. Don't worry, I'll give a new topic today itself. Okay, then that will be discussed in the next session. So, thank you all. Have a nice day.
Thank you,
Thank
sir.
you, sir.
Chat